Here we're looking at a driver's speed across a speed trap, and in part A we would simply like to know was the driver speeding by how much on average. So far we only have that the driver took 7 minutes to do 5 miles. So we want to have miles per hour in our calculation. However, we don't have the hours, we do have the total miles, which we know is 5. So how many hours do we have? Well, we have 7 minutes, and 7 minutes represents 7 out of 60 minutes, which forms an hour. So it's 7/60ths of an hour. So this is a real quick way to do it. Otherwise, you could do 7 divided by 60 and plug that number in down here. So we'll type this in, being careful to have parentheses for the 7/60ths, just to ensure that our calculator understands that that's all in the denominator. And we have that the driver's going about roughly 43 miles per hour. Okay, well, it looks like the driver was speeding a little bit. He was about 3 miles per hour over the speed limit. By about 3 miles per hour. Now that's just an average. In part B, we're asked to imagine the following data is collected on this particular driver via the availability of a satellite system. And so here we have different times and then the total distance traveled from one cop car to the next. So we see that at 0.025 hours after passing the first officer, he had gone a total of 1 mile. We want to approximate the instantaneous rate of change, i.e. the speeds, for the vehicle at each of these different times here. Now there are different methods we can use to approximate this because we don't really have anything in between 0 and 0.025. So one way is to, well, let's just visualize this real quickly. We have 0, 0.025, 0.05, 0.075, and 0.1. And then we have 0, 1, 2, 3, 4, 5. So here's what's happening. At time 0, we're at a distance of 0. At time 0.025, we're at a distance of 1. And then 2.5. And then we're at 4. And then we're at 5. So maybe not totally clear, but it looks like maybe we're getting something like this. Not quite linear. And so one way to do this is to approximate the rate of change at 0.025 is either to use the 2 points surrounding it, so that we would get something like this, or we can just use this point and the point itself, which is what we'll do. So again, there are kind of a bunch of different ways to go about this, but we'll take 1.0 minus 0.0, and this is miles. And what was the span of time there? Well, it was 0.025 was when 1 mile was recorded, minus 0 when the 0.0 miles were recorded, and that's 1 divided by 0.025, which gives us 40. So that gives us an estimate of 40 miles per hour between 0 and 0.025. So that's our estimate for 0.025. So it's just an estimate. There are a lot of ways to do this. There's not really a precise, more precise way to do it because it can kind of change from situation to situation. So for 0.05, so for this guy right here, we'll use this point and this point. And what will that give us? Well, this point right here corresponds to 2.5, a distance, minus the nearby point, which is 1 mile, so that's this point right here, divided by the difference in time, which is 0.05 minus 0.025, and that will come out to approximately, well, let's just do this all in one punch, 2.5 minus 1 divided by 0.05 minus 0.025, which gives us 60, a speed that's much faster, 60 miles per hour between those 2 points. So going much faster at this point, and so definitely have an incidence of speeding. And now we would do the same thing for 0.075. So for 0.075, we would just use these 2 points here, 4 minus 2.5, divided by 0.075 minus 0.05, excuse me. And that gives us, I believe this can come out the same as before. Divide that by 0.075 minus 0.05. And that gives us, again, 60 miles per hour. And finally, we would repeat this for 0.1 hours. And that would give us 5 minus 4 miles divided by 0.1 minus 0.075 hours, which would give us 1 divided by 0.025. Do that subtraction, and that comes out to 40 miles an hour. So a little bit slower. So obviously speeding quite a bit. So we want to determine out which of the moments was the driver speeding. It definitely looks like he was speeding around 0.05 and around 0.075. Then we're further asked to look at this data, which is now in closer proximity. So notice that these data points are really close together. And we want to use the alternative method, which is basically using the point itself, 0.05, 2.483, and then the nearby point. So fixing this point and then finding the rate of change between it and the others. We want to approximate the driver's actual speed at 0.05 hours. How does this answer compare to your estimates from the original table given in Part B? Okay, so what we'll do is we'll find the rate of change between this guy and this guy. So we'll have 2.483 minus 2.160 divided by 0.05 minus 0.045. So this is our far estimate. Why do we do this? Why not just pick the closest points nearby? Because we want to make sure that the behavior of the slope is not doing anything really strange. We want to make sure things look pretty smooth. So we'll plug that in. I'll come over here and do 2.483 minus 2.16. Divide that by 0.05 minus 0.045. And we get about 64.6 miles per hour. Guys, remember, we're dividing miles by hours. And then we would do the same thing for the next pair. So between this and this, we'd have 2.483. And notice now we're just getting more precise. We're doing exactly the squeezing in of the points. Here's what's happening at 0.05. And now we're picking a point here, finding the average rate of change, picking a point even closer and finding the average rate of change. So we're getting a better estimate of what's actually happening at 0.05. So subtract away 2.418, divide that by 0.05 minus 0.049, and that gives us, let's see, I'm going to pull up my last answer so I don't have to do too much typing. I'll just change this to 4.1, I'll insert an 8, and we'll do 0.05 divided by, or minus 0.049. And that gives us 65 miles an hour. Okay, well that means we have all the underestimates. It does appear that the speed's getting faster at around 0.05, but just to make sure that our estimate is going to be right, let's figure out what happens after 0.05 hours. So let's figure this out right here. In other words, we have 2.547 minus 2.483, and we're going to divide that by the difference in time, which is 0.051 minus 0.05, and that gives us, drum roll, 2.547 minus 2.483. Divide that by 0.01, which is actually the difference between 0.051 and 0.05, and that gives us I think I might have made a mistake here. I think it should be 0.001. I think that's our problem. 0.001 and that gives us 64. Okay, and let's just, so it looks kind of interesting here because it appears that our slope goes from 64.6, it goes up to 65, but then it goes back down to 64. So let's just ensure that we're considering this correctly, and now just find one more rate of change between 0.05 and 0.055. So we have 2.806, which is the output at 0.055, minus the point that we're keeping fixed, the point of interest. Divide that by the difference in time, which is 0.005. That's 0.055 minus 0.05 gives us 0.005. And we will do 2.806 minus 2.483 divided by 0.005, which gives us 64.6. Okay, well, what's happening here? Why is this behaving so strangely? It goes from 64.6 to 65 to 64 to 64.6, and chances are we're experiencing a little bit of rounding issues, that this data probably has some extra rounding taking place. That is, if we had more decimal places, we'd probably see more consistency. And this sometimes happens when you're working with the instantaneous rate of change and you're really compressing points very close together. Rounding is key. So we would guess that that in actuality we would probably conclude that the speed limit is somewhere maybe between 64 and 65 miles per hour. So somewhere in there. And without actually doing anything more mathematical, we'd pretty much have to stop there.